Welcome to another episode of Learning. Please like my videos and share them with your friends and colleagues. Please join as a member in my channel and support me in my channel. Yes, this is my channel. Please subscribe my channel if you have not already subscribed. Thank you. Right, we start discussing the solutions of the problems that have appeared in the IIT JAM Mathematics Exam 2024. In this video, we discuss two problems from the section Algebra, in particular from group theory, and these questions are question number 5 and 6 from the question paper. And these two questions are suitable for all these examinations. The JL, Junior Lecturer, Degree Lecturer, TG Set, AP Set, CSR Net and GATE exam. And my advice to all our aspirants of CSR Net is that you study these problems and prepare a good notes on it, and they will help you. And many a times the questions of the IIT JAM are coming in CSR Net examination with some slight modifications, and you take this my advice seriously and work out the problems that I am explaining in these videos. Right. This is the question number 5. And the question is, let G be a group of order 39 such that it has exactly one subgroup of order 3 and exactly one subgroup of order 13. Then which one of the following statements is true? We are given 4 options. Option A, G is necessarily cyclic. Option B, G is abelian but need not be cyclic. Option C, G need not be abelian. Option D, G has 13 elements of order 13. Let's now discuss the solution of the problem in detail. We are given a group G. Its order is 39. We are given G has exactly one subgroup of order 3, say H. In our BSc, we might have studied this problem. The problem is, let H be a subgroup of a group G. For any A belongs to G, let A capital H A inverse is equal to the set of all elements A small h A inverse, where small h comes from capital H. Then A capital H A inverse is a subgroup of G, and the order of A capital H A inverse, that subgroup's order, is the same as the order of H when H is finite. Now, as seen here, A capital H A inverse is a subgroup of G of order 3 because order of H is 3 for any A belongs to G. So, since G has exactly one subgroup of order 3, we must have A capital H A inverse is H itself for all A belongs to G, because G has exactly one subgroup of order 3. So, A capital H A inverse is equal to H for all A belongs to G will imply H is a normal subgroup of G. And we are given G has exactly one subgroup of order 13, say K. As above, K is a normal subgroup of G. Right. Now, we have H is a normal subgroup of G, K is a normal subgroup of G, and the GCD of order of H, order of K is the GCD of 3, 13 because order of H is 3, order of K is 13. The GCD of 3 comma 13 is 1. They are relatively prime. Then we have studied in our classes that G is isomorph, G is equal to, G is the direct product of H and K. Some people say the H cross K. G is H cross K. Right. We continue in the next slide. And we have seen G is H cross K, the direct product of two subgroups, H and K. And note that H is H is cyclic. Why? H is of order 3. 3 is prime. Every group of prime order is cyclic. K is also cyclic. Its order is 13, where 13 is prime. And every group of prime order is cyclic. So note that H and K are cyclic since they are prime. They are of prime orders. So H is isomorphic to Z3. H is a cyclic group of order 3. Z3 under addition modulo 3 is also cyclic. So H is isomorphic to Z3 and K is isomorphic to Z3. Any two finite cyclic groups of the same order are isomorphic. That's the reason. So now you got H cross K is isomorphic to Z3 cross Z13. But now note down, Z3 is cyclic, Z13 is cyclic. Note down the GCD of 3 comma 13 is 1. Then Z3 cross Z13 is not only a group, it is cyclic. It is cyclic. Further, its order is order of Z3 cross Z13, that is 39. And it is cyclic. Z3 cross Z13 is cyclic. And we know for 39, we have Z39 is also cyclic. And we know any two finite cyclic groups of the same order are isomorphic. Therefore, Z3 cross Z13 is isomorphic to Z39. Z39. Since any two finite cyclic groups of the same order are isomorphic. So that's what happened. G is isomorphic to Z39, where Z39 is cyclic. Therefore, G is necessarily a cyclic group. Therefore, option A is true. Right. Option B and option C are not true. Option B is not true because it says need not be cyclic, but it is cyclic. So option B is not true. And option C says G need not be abelian. It is cyclic, therefore it is abelian. Therefore G, it's abelian. So G need not be abelian. Option C is also not true. Options B and C are not true. And now note down K. K is the G has exactly one cyclic group of order 13. And in this group, except the identity, every other element, every non-identity element of K, they are of order 13. Every element is of order 13. Thus, there will be 12 elements in K which are of order 13. Right. Since K is the only subgroup of order 13 of G, and each non-identity element of K is of order 13. Therefore, this shows that G has 12 elements of order 13. But in option D, it is given G has 13 elements of order 13. This is not true. Therefore, option D is not true. Summarizing all the options, the answer to this question is option A. That is the detailed discussion of the solution of this given problem. And in this, we have not made any effort of using Solo's theorems in any manner in this. And in fact, Solo's theorems are not required here. But Solo's theorems are not used because it is not included in the BSc syllabus. Agreed. We move to the next question. Right. Now we take up the next question, question number 6. For a positive integer n, u of n is the set of all R bar. R bar is, bar denotes residual class of residual class of R in integers. So R bar belongs to Zn, where the GCD of R comma n is 1. Be the group under multiplication modulo n. This is given to be a group under multiplication modulo n. Now then, which one of the following statements is true? We are given 4 options. Option A, U5 is isomorphic to U8. Option B, U10 is isomorphic to U12. Option C, U8 is isomorphic to U10. Option D, U8 is isomorphic to U12. Right. Let's now discuss the solution of the problem in detail in the next slide. Right. We have small n belongs to capital N. It is a natural number. We have U bracket n is residual classes modulo n. R bar belongs to Zn, where the GCD of R comma n is 1. It is given that it is a group under multiplication modulo n. Agreed. Now let's take the first one. U5. 5 is a prime number. And what are all those numbers? What are all those which are relatively prime to 5? There is 1, 2, 3, 4. 1 bar, 2 bar, 3 bar, 4 bar. Residual classes. In this, you take 2. 2 square is 4. 2 cube is 3. 2 power 4 is 1. They are all multiplication modulo 5 you have to do. 2 square is 4. 2 cube is 8. 8 modulo 5 is 3. 2 power 4 is 16. 16 modulo 5 is 1. So it is a cyclic group generated by 2 bar. And Z4 is also cyclic. Is also cyclic group of order 4. Both are U5 and Z4 are cyclic groups of the same order and they are finite, therefore they are isomorphic. Now take U8. 8. So now is 1 relatively prime to 8? Yes. 2? No. 3? Yes. 3 comma 8 is 1. 4? No. 5? 5 comma 8 is 1, right? 6? No. 7? Yes. 7 comma 8 is 1, right? 7 comma 8 is 1, right? So now in this, 3 square modulo 8 is 1. 5 square modulo 8 is 1. 7 square modulo 8 is 1. Right. This is. And 3 multiplied by 5, 15 modulo 8, 7. 7. 3 multiplied by 7, 21 modulo 8 is 5. 5 multiplied by 7, 35 modulo 8 is 3. So you get these things. Now, do you remember anything after seeing this one? We have a group called Klein's 4 group, which has 4 elements: A, E, A, B, C. A square equal B square equal C square. AB is equal to C. AC is equal to B. BC is equal to A. So that is the one. So therefore, it is none other than it's isomorphic to K4. U8 is isomorphic to K4. Right. Now, can U5 be isomorphic to U8? No. U5 is cyclic. U8 is abelian but not cyclic. Therefore, U5 is not isomorphic to U8 because U5 is cyclic and U8 is abelian but not cyclic. So, option A is not true. Right. We move to 3, U10 we take. What are all those numbers which are relatively prime to 10? 1, bar, 3 bar, 7 bar, 9 bar. And 3 square, 9, 3 cube, 27, modulo 10, 7, 3 power 4, 81, modulo 10 is 1 bar. So 3 generates every element of this one. Therefore, it is a generator. It generates. Therefore, U10 is a cyclic group generated by 3 bar. U10 is of order 4. Z4 is a cyclic group of order 4. And any two finite cyclic groups of the same order are isomorphic. Therefore, U10 is isomorphic to Z4. Right. Now, we told U8 is K4 is isomorphic to K4. U10 is isomorphic to Z4. So, can U8 be isomorphic to U10? No. No. U8 is not isomorphic to U10 because U8 is not cyclic because it is Klein's 4 group. U10, it is cyclic. So, it is option C is not true. Right, we move to U12. Now, elements which are relatively prime to 12 are 1 bar, 5 bar, 7 bar, 11 bar. And 5 square is 25 modulo 12, 1. 7 square, 49 modulo 12 is 1. 11 square is 121 modulo 12 is 1. 5 into 7, 35 modulo 12 is 11, etc. 5 into 7 is 11, 7 into 11 is 5, 5 into 11 is 7. Agreed. So it's just like this, Do it. It is isomorphic to K4, check. Right. Now we ask the question, can U10 be isomorphic to U12? U10 is cyclic. U12 is Klein's 4 group. They are not isomorphic. So U10 is not isomorphic to U12 since U10 is cyclic and U12 is not cyclic since it is being a Klein's 4 group. So what is left out? Option D. U8 is isomorphic to U12. Why? U8 is isomorphic to K4. U12 is also isomorphic to K4. Therefore, U8 is isomorphic to U12. So, option B is not true. U10 is isomorphic to U12. It's not true. And now, U8 isomorphic to K4. U12 is isomorphic to K4. Therefore, U8 is isomorphic to U12. Therefore, option D is true. Right. Summarizing all the options, the answer to this question is option D. That is the detailed discussion of the solution of these problems. I'm sure you appreciate the arguments and the proofs given here. I am sure that you understood the solution of these two problems. Thank you for watching this video now. Please like my videos and share them with your friends and colleagues. Please join as a member in my channel and support me and my channel. Yes, this is my channel. Please subscribe my channel if you have not already subscribed. Yes, I am sure I will be meeting all of you once again in another episode of learning. Enjoy learning mathematics. I wish you all the best. Thank you.